we were discussing the 4 quantifier laws. Out of that we have really completed 2 of them, the simple ones. One was universal specification, another was existential generalization. Then we have to discuss the other 2. So, one of them, the universal generalization, we have discussed, right, but proof was informal, we have not proved it completely. Next our job was to formulate existential specification itself. Okay. So, formulation for universal generalization was okay. So, let us rewrite it again. So, we start with a set of formulas and X a formula. Then from X we want to go for every X, right, that was the point. So, our formulation was if X is a variable that does not occur free in any formula of sigma, then we had from sigma entails X we can go for sigma entails for each X. Okay. That was our universal generalization. So, all that we need is if X is not free in sigma in the premises, if X is not free in the premises, then you can go for generalizing over that particular variable X, that is the crucial point. Then we wanted to formulate existential specification. Here again our motivation was in arguments when you have one premise, for example there is X P X, you use P C, where C is one ambiguous name, we do not know exactly to which element in your domain it refers, but it can refer to one of the elements, that much we know. So, it is an ambiguous name, right. Then we just write P C. Now, from P C and along with other premises we conclude that something say Q C, right. Then from Q C we generalize, or even if there is no C at all occurring in the conclusion, then whatever you have concluded that follows from the original, that was our point. Okay. So, somehow this ambiguous name is eliminated in the proof. Okay. So, that means suppose you have sigma as the set of premises, then you have sigma along with there is X P X. So, from there you conclude some Y, right. Then you say that from sigma and there is X P X also follows Y. Is it clear? So, the whole proof methodology goes like this: you have there is X P X, but you cannot say that there is X P X entails P C. So, you start with sigma along with P C, right, in for Y. From this you conclude that sigma along with there is X P X also gives you Y. Is it clear? So, that means it would look something, the conclusion of existential specification would look something like this: sigma union some formula entails Y, then sigma union there is X X entails Y. Is it okay? So, along with the premises you have really starting from this, you are starting from this in your proof, but you know what this there is X X will give the element, we do not know exactly. So, we just take one ambiguous name C and instantiate this. Now, from this along with the premises there follows Y, therefore, we conclude from this follows Y. It is a bit complex in this formulation, but while using this is what we do, right. So, let us formulate it. Here what are the constants we need? That this constant C should not occur in sigma, right. Why is it so? Suppose you have already told Socrates is something, now you say there exists a man with this property. Can you tell Socrates is also that having that property? We do not know, unless anything specific is told about Socrates, right. So, this C should not have occurred in sigma, and then our proof procedure says that the C has been eliminated in the proof somewhere, so that we get Y. That means C also does not occur in Y, fine. Well, there is also one more constant. Suppose in X itself originally there is C, okay. For example, P x C, there is X P x C. We cannot say there is X P x C will give you P C C, that C can be different now, right. So, that means this constant is completely new, it neither occurs in any formula of sigma nor in X nor in Y. Is it clear? So, now we can formulate by writing these conditions. Let sigma be a set of formulas X, Y formulas let C be a constant that does not occur in any of sigma or even X or Y. Okay. Now, if sigma union X X by C entails Y, then sigma union there is X X entails Y. See, this constant anyway is being eliminated. So, instead of a constant you can also take a variable, is that right? It is just a symbol, that symbol should not have occurred, that is the main point, right. So, we may have also or a variable. Once it is a variable and you say the variable does not occur, it means the variable does not occur free due to renaming, right. If that variable occurs bound, you can also rename it equivalently. So, it will amount to a variable that does not occur free, both will be acceptable, right. So, let us now prove them. So, this proof of universal generalization we have already discussed, okay. Let us give a formal proof now. So, how do we proceed? So, let us do it by contradiction, it may be quicker. So, we want to prove sigma entails for each x x. So, we will start with one state which is a state model of sigma and try to show that that becomes a state model of for each x x, right. So, by contradiction if we want, we take one state model of this which is not a state model of this, right. So, suppose I L is a state which satisfies sigma, but I L falsifies for each x x, right. So, once I L falsifies, it means there exists one element in the domain of the interpretation under which I L is a state such that I L x fixed to D does not satisfy x, right. Is that okay? So, we want falsifies. So, that means then for some element D, so I am not writing it completely, this I L assumption is I equal to D phi, L is one valuation under that. So, for some element D in D, I L x fixed to D falsifies x, right, because when you come to IL satisfies for each x, that will mean for each element D in D, IL x fixed to D satisfies x. So that is not, that does not hold. So there is at least one element, for some element IL x fixed to D does not satisfy x, just from our formal semantics, whatever way we have introduced the semantics. Fine. Okay. See, we have to use this sigma entel x somewhere. So once you say IL satisfies sigma, it is the same thing as telling IL x fixed to D satisfies sigma. Why is it so? Because x does not occur, right, does not occur free in any formula of sigma, x itself does not occur. So that is your relevance lemma, right. If x does not occur, then whatever value you fix to it, it does not matter whether it satisfies or not, will be fixed by the original valuation, right. So we see now that IL x fixed to D satisfies sigma due to relevance lemma. Right. Otherwise you can see what is its effect. L and L x fixed to D work the same way on sigma, that is what you want to see, right. X does not occur and L x fixed to D agree on every variable except x, x does not occur, right. So this satisfies or IL satisfies are the same, that is exactly relevance level. Okay. So now you see IL x to D is a model of sigma, state model of sigma, but it falsifies x. This contradicts the assumption, right. This contradicts sigma entails x, that is it. Now short proof comes because of proof by contradiction. Now proof for existential specification is also similar, and here all that we have done is x actually occurs in capital X, right, otherwise x to D will be vacuous. If x does not occur, then x or for each x are equivalent by empty quantification. So there is nothing to prove. Okay. So we leave that uninteresting case. Similarly here, if your x does not occur in X, right, so that also becomes vacuous, there is nothing to do. These and these are the same, both of them are x only, equivalent to x. Okay. So how do we proceed here? Again we want to show sigma union there is x entails y, right. So we start with one state which is a state model of sigma union there is x. So this means IL is a state model of sigma, okay, and IL is also a state model of there is x. So that means IL x fixed to D is a model of x for some D in D, right. Okay. This is the meaning of the existential quantifier there is x. Is that right? We want to show this entails y. To show that entails y, we have to use this, because we already know this entails y, right. So sigma is okay, IL is there, but x by c, that is to be seen. Now this c is new to whole of sigma x y, c never occurred, right. Now L never interprets c as it is, right. So what do we do? By relevance lemma we take the minimum things, only L is exactly appropriate to whatever is there, right. So because c is not there, so we can extend this L, it has to be interpreted, right. So what do we do? Extend L to L prime. So once we say extend, it means whatever L assigns to variables and constants, all the terms they have been kept as it is, we are giving some extra, right, and calling it L prime. So, L prime by taking L prime of C equal to this deal, because we want this to satisfy, right, this formula should be satisfied, we have already something like that. So, we take L of C, L prime of C equal to D itself, is that right. Now, what we see, I L satisfies sigma, it is same thing as telling I L prime satisfies sigma, L and L prime agree on everything except C possibly, and C does not occur in sigma, that is again relevance lemma, right. So, what we see is I L prime satisfies sigma, right. Now, I L x fixed to D satisfies x, right. Suppose it is like P x. So, I L x fixed to D satisfies P x, that means when you substitute x in terms of D, it says D belongs to phi of P, right, that relation D belongs to phi of P. Now, look at this, L prime satisfies this, means what, in P x you have substituted x as C, so it is P C, right. Now, L prime of C equal to D, so this also says D belongs to phi of P, is that okay, because L prime of C is the same thing as L of x fixed to D, they are evaluated the same way, fine. So, what we see is I L prime satisfies x by C, right. Now, since sigma union x by C entails y, here is one state model of sigma union x by C. So, that state model should also be a state model of y, that state should be a state model of y due to this, is that clear. So, we conclude that I L prime satisfies y. Okay. Now, I L prime satisfies y, L prime and L agree on all the variables constant except possibly C, and C does not occur in y, right. So, again due to relevance lemma I L satisfies y. That is what we wanted to show. Is it clear? So, you start with one L, valuation L, you get the state I L, then I L satisfies the rejects x, therefore, you have one element D, such that I L x fixed to D satisfies x. Now, if you define your L prime such that L prime of C equal to D, then it is equivalent to telling I L prime satisfies x by C. Okay. Then use sigma union x by C entails y to conclude I L prime satisfies y. Now, since C does not occur in y, I L prime or I L satisfy or do not satisfy, right, they agree. So, it is equivalent to telling I L satisfies y, that is what we wanted. Is clear. So, now that all the 4 quantifier laws are proved, you need not even go through all the other laws, right, you can prove them by using these quantifier laws, that should be easier. But there is a hitch, it is this existential specification is not in its full generality, it is not very general. Why? For example, you say for each x there is y p x y, okay. Fine. So, here to capture this existential generalization, existential specification, you need really y to be depending on x, right. You choose one x, for that x you get some y such that p x y holds, you choose another x, it need not be the same y, right, for the new x. So, y is really dependent on x, but this form of the existential specification says that you will be using the same C for everything, right. Though it is not same, it is ambiguous, it can vary, but it does not show up. Okay. This dependence has to be shown somehow, we will do that later, we will wait for some time to come to this generality. Now, for our purpose this is enough. Okay. Let us see some examples how to tackle the consequences by using these quantifier laws. Okay. Let us take one easy example, say so that this sentence is valid, that should be easy. Okay. So, how do you propose to go? See, look at the inside of this quantifier for each x. Think of not p implies q implies not q implies p, that is a propositional tautology, right, contraposition and double negation. Okay. So, from a tautology you should get it, but you get what? You get only not p x implies q x implies not q x implies p x, that is all. Then universally generalize, right, to reach out for each x, fine. So, we start say this way, we say top is equivalent to not p x implies q x implies not q x implies p x. So, justification is tautology, or we will write just p l from propositional logic. Okay. Then what do you want to say? From this we will follow not p x implies q x implies not q x implies p x, and you want to use universal generalization. Now, what will you write here in a calculation? It is not equivalent. Okay. This side entails this, yes, but from this does not entail, p x does not entail for each x p x, right. But you want to use universal generalization, which says if x is a variable that does not occur free in any formula of sigma in the premises, then you can conclude. So, now you see this x on which you are quantifying, universally quantifying, that does not occur in the premises, there is only one premise here, right. So, you can use universal generalization, but then what to write there? What symbol we will write? Okay, we will devise one symbol, we will write like this. Okay, we will write implies, because this is not entailment. So, what is that we are really writing it here? It is a meta sentence. If from all these things x follows, then from all those things for each x follows, that is what we are writing. And it is not x entails for each x. So, what is the difference between them? You have x entails for each x, another is sigma union x, or let us forget sigma, take it empty. We say if x is valid, then for each x is valid. So, if you have sigma, you will write sigma here, sigma here, sigma here, sigma here also. Okay. Fine. So, now let us look at these two sentences. This is a meta sentence, this is also a meta sentence, but it is of different level, still a higher level. It involves talking about the entailments itself. This talks about validity, this talks about entailment itself, right. So, it is still a meta sentence, it talks about entailment relation itself. Now, what does it say? This says x entails for each x, means whatever state you take, if that is a state model of x, then that is a state model of for each x, right, or you may say for each I L, if I L satisfies x, then I L satisfies for each x x. What does this say? Now, if then and this for each are interchanged. This says if for each I L satisfies x, then for each I L satisfies for each x x, right. So, there is some difference. This can be vacuously true if there is one state which falsifies it, right. For example, I say if P x is valid, then Q x is valid, that is true, right, because P x is not valid. Is it okay? So, it can be very vacuous, but this one is stronger. If this holds, then this will hold, not conversely, right. Now, in the calculation we want to write this sentence: if sigma entails x, then sigma entails for each x x. It is not entailment, it is weaker than entailment, okay. Entailment is stronger. So, that is why we write some another symbol, let us call it implies, read it as implies. In mathematics this is the symbol we always use, right. It means exactly this: if from all those premises something follows, then from all those premises the other thing follows, okay. It is not really entailment, the implies in mathematics, okay. Now, what happens is it says it is not only connecting the previous line as per other symbols in the calculation. In a calculation we can use equivalence, we can use entailment. These two symbols connect to the previous line always, right, but this symbol implies does not connect only to the previous line, it connects the whole proof before it, whole calculation that has gone before it. If all those things hold, then the next one holds, right, that is the difference. So, therefore, you can write this with an indentation. If it continues, if the last line it does not matter, it is all right, but if it is not the last line, you need another sub calculation here. For example, while applying existential specification, something else you are assuming here which is not given, you require to prove this, right. And now, in this context x by c becomes an extra premise, right. Of course, it has connection with this, but it is an extra, it does not appear in the premises, fine. Now, this one you assume, continue, find y, then you conclude this. So, that proof or sub calculation itself will slightly push to the right, make one indentation to remind that it is a sub calculation we are entering. After this we will come to the original, right. We will see an example how it is used. Say so this we want to prove, okay. Now, you see this x can be out of this, right, because here it is a sentence that itself where x is not free. So, you could have written this x outside also, does not matter, which means we can take remove this bracket, that is what it says. Okay. Now, suppose you want to prove it by calculation, then first you will be using deduction theorem, because it is a serial implication, something implies B implies C, right. So, you say by deduction theorem we show, due to deduction theorem it is enough to show for each x P x implies Q x, there is x P x entails there is x Q x, okay, which is same thing as taking AND here also. Fine. So, till now it is propositional only, reduction theorem. Then we have to give a proof of this. Fine. So, how do you go? Where to start with? You may be starting with there is x p x, because that C I can use it here to specify for each. Okay. So, let us write this way, there is x p x and for each x p x implies q x. I start from there premises. Now, I want to use existential specification, I write P C, but I cannot write P C, right, because from there is x p x P C does not follow, okay, but I can use P C. So, extra premise I have to take. Then I will say that my existential specification starts here with this C, begins with this new constant C, right. So, I say this implies, let me indent it here, implies I can have there is x p x or for each x p x implies q x and P C. It is something like in your reduction theorem, in informal proofs you take on added premise and then finally you finish, come to that added premise implies your conclusion, right. So, this is an added premise I am taking now, with sigma I take P C. Now, sigma here does not include there is x p x. So, if it is really confusing, you may not start even with there is x p x, start with P C itself, right, but that will not give you any hint why you are starting with P C, fine. So, let us keep it as it is. Now, then what do we do? We go for universal specification here. So, we write U S, this entails there is x p x and this we write P C implies Q C and P C. So, this universal specification we are using by taking x as C, x is substituted by C here. Okay. So, this one is equivalent to writing C is new, I am going to introduce C, which is a new constant. Now, from these two I will use modus ponens to get there is x p x and q c. Okay. Is that right? So, now from q c we will go for existential generalization. So, this gives there is x p x and there is x q x from q c, fine. Okay. So, now what it says, this new formula what you have got has no C, there is no C here. Okay. Since there is no C, our original formulation of existential specification says if there is no C finally, which is our y now, that y is there is x q x here, then you can say sigma union there is x x entails y, right. So, this gives you entails, you can say there is x q x. This is AND anyway, but this AND is immaterial, we never used it anywhere. All it will say is there is x p x and this one will entail this there is x q x. Is that okay? So, what do we do here? Our existential specification ends, fine. So, we repeat it again, we say entails there is x q x, telling that it is existential specification with C ends here. fine. Is it clear how we are going? So, this indentation will tell us that from this step to this step it is only a sub calculation, we could have done it outside. Instead of bringing in there is x p x also, you can just start with P c and conclude there is x p x. After that you say there is x p x and this entails there is x q x. Is that okay? That is what we are going to do. So, that means in every step you even could have deleted this there is x p x. Because it is a sub calculation. So, you start with P c and then continue find there is x q x. So, all it says this is your sigma union P c entails there is x q x. Therefore, sigma union there is x p x entails there is x q x. Okay. Can you read the proof now? Where you have to read the theorem of existential specification now. It says from this indented sub calculation, it says sigma union P c entails there is x q x. Okay. Therefore, sigma union there is x p x entails there is x q x. Okay. Side by side you can also give informal proofs. Now you are matured, we can do both the things at a time. So, this one we could have started with top, I am just rewriting it to see it as an informal proof. Then by P L it follows not P x implies q x implies not q x implies P x. Okay. Now, in informal proofs we will not start with this top, we can say why it is valid, right. So, top entails this, that is how we are doing it. So, top is this, then this justification will be written here instead. In calculation we write previous step. So, that what we are going to do it says. Now, here we are giving justification, not we are going to do, but what we have done. So, here we have simply used P L tautology. Then third one we simply write for each x not P x implies q x implies not q x implies P x by universal generalization. This is what we wanted to prove, right. So, our proof says that we start with P c, right. So, we say here justification has existential specification with C begins, which can be one extra assumption. Okay. Before this, if you want to list all your premises, you can keep it, informal proof allows that, right. So, it is wiser to start with all the premises listed, fine. So, instead of this we will start with 1 for each x P x implies q x, 2 we will write there is x P x, all these are premises, or let us write hypothesis rather than premises to not confuse with our P. Yes.
Informal, because you are bringing the PC in.
Informal proof has some formality. So, it does not use those symbols, entailment or equivalent symbols.
Yeah, but that is also not completely formal.
Calculation is also not formal, right, but calculation can be made formal. Similarly, informal proofs, they are just different styles, right. Problem is in calculation you have to connect with the previous lines in P L. Informal proof has some more informality. You can just use any premise anywhere, does not matter. Okay, that is the difference. Here in calculation you can show what is equivalent to what entails from where and so on. In informal proof it is not equivalence, it is only entailment, there is another difference. Okay. So, let us see how does it proceed. So, this will be our third line now. Here it starts, because there is x p x is there, we start with P c, it does not follow from it. So, we have to write it specifically that it does not follow, but it is one extra premise we are adding due to existential specification. Then we instantiate from 1, it says P c implies Q c, 1 universal specification. If you want to mention how you specified, you may write x by c, x has been substituted by c, just to say what is the specification. Then we use modus ponens as earlier. So, 3, 4 modus ponens, and then 6 there is x q x, from 5 existential generalization. Okay. Now, you get a formula y which is independent of this ambiguous name or new constant c, fine. Therefore, we say once more we have to write there is x q x, it follows from the premises where your existential specification ends. Is that okay? That is how it will be proceeding in informal proofs. Let us take one more example. Let us see whether this has a proof or not. Okay. So, can we try one informal proof first? Okay, let us see. So, what is our plan? We want for each y q y. So, we should be able to get q y from somewhere. Now, how to get q y? From this anyway. This will come from there is x p x. So, I can have P c, then I instantiate c with this, I get for each y P c implies q y, then P c is not having y. So, I can use my distributive law, right, take that out. So, I get for each y q y directly, I do not need universal generalization here also. If you do not want, you can instantiate that y, if you do not want to use distribution, instantiate that y, get P c, apply M p, get q y for each y q y. Is that okay? So, let us write it. So, I start with this one, premises, it is a premise. Second, there is x p x is a premise. Next, I want to use existential specification. Okay. So, I say P c. Fourth, for each y P c implies q y from 1 universal specification. Then I say P c implies for each y q y distribution, 4 distribution. Next, P c and this gives for each y q y 3 5 modus ponens. Okay. Next, since you have got it, you do not stop it here. If you stop, it will say for each x for each y P x implies q y and P c gives for each y q y, because this is an extra premise you have used, it has to go, right. So, next is for each y q y. So, we will write E S C E. Now, in order that this is concluded, you should have a premise there is x p x, right. If it is not a premise, then it cannot be concluded. You see that. So, along with this, better write what premise you have used, right. So, similarly here E S C E, you are using that as a premise, there is x p x, right, but in a calculation anyway we have to see it, we do not refer it back. In informal proof you can read it where it is really used. So, for example, here when you write there is x q x, better use 2, you are using that as a premise, that is why it is followed, otherwise it does not follow. Is it clear? Here for example, you have for each y q y, this follows with P C as a premise, right. Now, when you use extensional specification with P C and this to conclude there is x p x with this give you for each y q y. So, that means there is x p x is used as a premise now. Yes.
P x used for 3 itself.
No.
When you say P C,
It is not used because there is x p x never entails P C. That is the whole point in the extensional specification itself. Otherwise, we would not need extensional specification in that form, right. So, since it is there, we are taking this as the extra premise, but that is extra information, it does not entail. Okay. All it says is 1 along with 3 gives you 6, therefore, 1 along with 2 gives you 7, that is extensional specification. Is that clear? So, we mention 2 E S C. First symbolize this and then try to give a proof, whether you can give a proof or not. So, all that we have done today is use the laws, these 4 laws and earlier ones. So, there is one thing you can try in the proof itself. For the last one, instead of using distribution here, try to use the laws, these quantifier laws, and still conclude it, right, which will give you some confidence that I do not need to remember so many laws. These 4 quantifier laws along with the PL laws will be enough.